we're going to talk about in this talk is about cognitive models, cognitive computing, and its application to the world of fashion. So what is cognitive computing? And there's a fairly broad definition I put up there. It's basically reverse engineering the brain to build mind-like intelligent machines, right? This is a fairly well-accepted definition of cognition and cognitive computing. Something that I've added out there, which is embodied intelligence. So to me, cognition does not exist without some kind of interaction with it, whether the interaction is in the form of cars, self-driving cars, whether it's in the form of robots, or it could be simply the interaction through a web portal or an app, right? So cognition, the models that you're learning, you want to interact with them and you want to do something with them and then should respond to the interaction to the user. So that's what cognitive computing as a small definition that I would present out here. What this talk, as was mentioned that in the introduction, we are going to basically talk about connectionist models. So deep learning, I think everybody here would be aware of deep learning models, and what we are sort of going to motivate here is that how through some amount of neuroscience, I'm a pretend neuroscientist, so some amount of neuroscience, I'm going to sort of motivate why these deep learning models are actually biologically plausible, how they're biologically inspired, so some insight into it. And I'm going to talk primarily about computer vision as the main sort of area of deep learning models. The application that I'm going to talk about is a fashion. I'm going to not only talk about the models that we have learned for fashion use case, but also about systems that deliver these models and the systems that are efficient enough to deliver these models so that user interactions become rich and interesting. So connectionism basically is what deep learning networks are basically a connectionist model, right? So the idea there is that they are the behavior emerges because of the interconnection. So when you set up any neural network, you have neurons and then you connect the neurons in a certain way, and the connections have a certain amount of weights which you learn, and that's what gives rise to these properties of the neurons, of their neural network, right? The emergent properties of the neuron or the neural network arises not only because of the neuron properties itself, but quite often due to the weights and the way they are connected in the neural network. So the simplest example of, and the one that we are going to talk about today, because in computer vision that's the most relevant one, is the feed-forward hierarchical neural network that all of us have, I'm sure, have seen multiple times. And we'll show in this talk also. Now, as I said, I'm going to talk a little bit about neuroscience, and I'm just starting with that. So basically, in the brain, there are two types of interconnections between the neurons. One is what is called the white matter connection, which are the long-range, high-speed connections, and the other are the short-range connections, the gray matter, right? So the gray matter is your neurons. So this is a sort of a very simple diagram here. The gray matter is what are the neurons, which are basically the compute and memory nodes. So what is different between the neurons, which are the processors of the brain, and the processors that we are used to is that the neurons are basically have both compute and memory close by. There's no fetch of a RAM or a fetch of a disk involved in the neuron model, in the brain neuron model. The white matter is what connects, and as I show that it's what allows us to have this distributed functional areas. It's the wide area network of our brain, and it allows different parts of the brain to do different things. In the schematic diagram out here, basically all I'm saying is that there's a neuron and there's an electric signal which communicates between the two neurons, right? So the entire, one other thing which is fascinating about the brain, that there's only one code, which is spiking code, right? So every time something happens, it sends out a spike, which is an electric impulse, and there's nothing else. There's no other methodology in the brain to communicate between the processors. So there's a universal code which is going out, which is in terms of spikes. Just to sort of give a little bit more detail about biological neurons, it's the neuron cell body is what is a processor which basically integrates signals. So as we go to artificial neurons about 2 slides from now, you will see that there is a sort of a very nice simile between the biological neuron and the artificial neuron in terms of of how they are both similar in terms of integrating signals, right? So they both integrate signals. The biological neuron differs in the sense that it also has a timestamp associated with the signal it sends out. The artificial neural network that we talk about don't have timestamps. They basically are static in the sense they send out a value, but they don't send out a timestamp associated with with the signal. The other thing which is also going to be basically what we learn is I don't know if the pointer works here, but it's basically that gap out there. There are neurotransmitters in that gap, what you see between those two. So in the synaptic gap, there are these neurotransmitters, and these neurotransmitters modulate the signal flow, right? So from the axon is the incoming signal, which then gets passed on to the dendrite, which passes on to the cell body. The neurotransmitters basically modulate the signal, right? So they sort of change the signal in a certain way, whether they might allow the signal to flow through, they might modulate it by some weight, and that's how basically that's our memory. The synaptic, the neurotransmitters are what, the modulation of neurotransmitters are what capture the memory in our human brains, right, or in the primate brains. And this is again, we are going to see, so you can think of this as a weight, and this is a weight that we talk about in terms of neural networks. So these are the two things that I want to talk about, the neurons. The white matter is fascinating by itself because white matter is what allows this sort of distributed cognition to occur. So different parts of the brain, which is well known as, are responsible for different functions, right? So the back of the brain is responsible for vision, the front of the brain is responsible for planning and other coordination activity, side there's audition. This wide area network, which is provided by the gray matter, is what allows the different parts of the brain to occur, to basically focus on one function, right? So in this particular talk, we are going to talk about basically one function, which is computer vision, right? So and we are going to talk about why is vision difficult. So I'm standing here and I'm looking at people, and for me it's very, very simple, and this is something that takes a little bit of a sort of thought about why is computer vision that difficult? For us, it's very simple to say, okay, there are the tables, there's white cloth on them, there's blue this thing, and then each person out here I can more or less segment. If I pay a little bit more attention to them, I can figure out different attributes of the people sitting here. Computer vision has not reached that level by any definition. We can talk about deep learning having transformed computer vision, but still, if I give a photograph and I say, can you segment out the people and all the people here, and can you segment out, tell me what the tablecloth is, tell me what the color of the thing on the chairs is, it's going to be fairly difficult for a computer vision algorithm to do it. And we seem to do it very seamlessly, right? So computer vision is a challenging problem. And the problem in vision is basically it sees an image as basically a matrix of numbers. You don't know, but so what you input to a computer, when you take an image or a video or anything, you're just giving it a matrix of numbers. There's nothing else to it, right? And the vision algorithms has to basically process these numbers, analyze the numbers, and make sense out of it, the way we make sense out of it. A simple task, for example, is given these numbers, is to say that this is classified that this image has a cat in it, right? That this image is of a cat. So this is one of the simplest tasks that we are associated with computer vision. Why is vision difficult? Vision is difficult basically because of these variations, right? So again, right at the back, for me also it's difficult. The light is coming to my eye. I can't see people at the back because it's darker out there. I can't make out people. Right up in front, I can make out people much easier. There are people in different poses. You might see some frontal faces. You might see somebody's back might be turned towards you. But so then context obviously plays a lot of role in that kind of situations. Vision for computers, again, think of it that basically you're getting numbers, right? A matrix of numbers. This context, whether the person is in the front pose, back pose, what variations that they have, is quite difficult for a computer algorithm to make out of the numbers that are being presented. And the way people are solving this problem now specifically is basically they're thinking about it as a learning problem, right? A supervised learning problem. So there are multiple problems in computer vision. I'm just going to sort of talk about the simplest problem, which is classification, right? So the simplest the way people approach it, as I said, is by giving lots of training samples, right? So for cat, they have, we are showing about 12 examples, dog, mug, hat, and each of these have each class has multiple examples, right? So ImageNet, a very popular training set for computer vision, had 1 million labeled samples about 3 years ago, so it must be about, I don't know what it has now, maybe about 2 million or that. That's a huge number of training samples, right? Over about 1,000 class category. And basically, using these training samples, you want to learn the weights of a neural network such that you can classify an image into being cat, dog, or mug, or hat. I'm going to spend a little bit of time on this particular thing, and what this slide is showing is sort of, it's on the right is what would be a conjectured biological model, and the leftmost is what is a deep learning model, which is very commonly used nowadays, right? And in the middle is basically one of the first models that came out in 1989. So it's also very interesting to know that deep learning or versions of deep learning have been around since late 80s, right? So HMax and Neocognitron came about in 1989, 88 framework. It's only now that it's sure enough the depth of networks has increased, the number of training samples has increased, the power of computing has increased, but the ideas are more or less the same. So it's been a nice, like, from 80s coming back into 2000, something that doesn't happen often. Talking about the biological model a little bit more in detail before we go anywhere. So the biological model, and this is a conjecture, but I'll sort of show you another slide which is say that this is more or less true. So the biological model here sort of say that there's an image which, what you see on the V1, V2, V4, PIT, AIT, these are well-known regions in our brain. The V1 is the first visual area, V2 is the second visual area, AIT is some temporal cortex and so on and so forth. So what this conjecture is that basically the first visual cortex is filtering the image using very simple filters. Then it passes it on to another part of the visual cortex, which processes the image with slightly more complicated filters, and then it passes it on to another and so on. So you can already see the feed-forward layered architecture. So this conjecture, what the deep learning models do, is based on a conjecture from the biological models. People have conjectured that this is true, and that's what deep learning is implementing in a computational model. The other one is that feed-forward layered architecture. The other is as I said, V1 seems to be processing only very simple edge filters. If you look at it very carefully, V2 is processing a little more complicated filters, and in the AIT, you see these templates. So it is conjectured again that basically we in some part of our brain store templates, and this is true for faces for sure. We store template of our parents' face, we store templates of our kids' face, of a spouse face. So well-known faces, we store templates of them, and when the image is sort of processed through the AIT, it sort of matches the template and says, okay, this is my father, this is my mother, or this thing. So this processing, feed-forward processing, where we go from simple to more complex template, is also something which is being replicated by the deep learning models. If you look at deep learning models, you'll see that there's a very similar kind of a theme that is going on there. I'm going to take a quick pass to this. The deep learning model that I'm interested in for computer vision, which I use mostly for computer vision, are what are called the CNNs, right? The convolution neural network. The convolution neural network is basically, as I said, it's inspired by the visual cortex. It's basically a layers of operations, what we showed last time. Each operation is local. So basically, you're doing the box there is meant to sort of say there's a local template which only processes only certain parts of the image. And it uses the same common learned parameters, so the number of parameters don't go up that much. And each operation is performed by artificial neural network. So the three things that are there, layers, which we have talked about, local, common, and artificial neural network, neurons. And I'm going to quickly sort of show again that these things are real, what each of them mean. So the artificial neuron, all of people who have worked in the deep learning or neural network are fairly familiar with it. As I said earlier, it is an integrator, much like the biological neuron, right? It basically sums up all the signals that are coming in. There is a synapse, or what you can call a synapse, because we have a weight associated with the incoming signal, right? So there's a weight that you have learned, the W0, the W1s, and the W2s. And each of these are multiplying the incoming signals, which are then added. And then, given that value, it's passed to some non-linearity, and that's the output for artificial neural network. Very similar to the biological network, except for the fact that there's no timestamp, very similar. And the non-linearity could vary. You could assume that the non-linearity is more complex in the biological neurons, or there are various different forms of non-linearity, but fairly similar kind of this thing. As I said, the synapse are the weights that multiply, and what eventually the artificial neural network also do is learn these synaptic weights. What you'll do is basically you learn W0, W1, W2 to basically minimize some cost function. The cost function could be a regression cost function, it could be a softmax cost function, but that's what you end up doing, but doing some gradient descent or some other matter. Which is something which I'm not getting into, but it's not what the brain does. The brain is not by any this thing doing gradient descent inside it. It's sort of doing gradient descent on other things, but it's not doing gradient descent inside it to learn any synaptic weights. So there is a difference there in the learning mechanism that we are using. So again, just to concretize this thing, as I said, these ideas are fairly well grounded in what happens in biology. Convolution and layers both are shown to be biologically true. So Hubel and Wiesel in 1959 showed this by use of some biological experiment that there are local filters, or local templates in the brain, and they won a Nobel Prize for this. It's a very nice experiment, and there's a very nice YouTube video which explains it very well. So convolution does happen in the brain, maybe not by the same filters, but convolution operations do happen in the brain. This wiring diagram that I'm showing on the right is basically a fairly realistic, or fairly the details. There could be even more details, but it is the wiring diagram of the primate brain. So you have again these V1, V2, V4 areas and different areas in the brain, and basically this layered structures again hints at what happens in, or proposes what happens in the deep neural network field, right? Similarly, this simple cells and complex cells, this has also been shown by using of neuroscience and experiments in cats and rats, that these simple cells and complex cells do occur in the brain. So in this first sort of 20 minutes or so, what I had wanted to do, and I hope I got across, that the deep neural network that people are using in the computer vision algorithms are biologically realistic, and when we are talking about cognitive systems, we are talking about how to make more and more use of biological reality and biological plausibility, right, towards our models. So I just put in these two slides, they're kind of interesting, but the title of the slide is, this is a blog, and basically he's sort of talked about status of humans versus machines, right? So there are a bunch of different things where machines are supposed to beat us. One is in poker recently, lip reading, Go, and in 2015 image classification. So a bunch of these different tasks. I take I put it up, but I take it all with a little bit of salt, because I don't think it's a true thing. There are many things which differ from the way we learn. We don't need 1 million examples, or we don't need 1 million concrete. It's not that a kid goes through 1 million examples, then only learns what an apple is, right? You maybe give a couple of examples, and then over the period of time, you get more examples from a different context, hints from different aspects of your life, and that's how you learn. You never sort of page through 1 million examples and get things. We don't require that. We'll talk about it. What is the energy consumption of the brain, right? Do you think about that? Then at the end of the day, the multitasking, whatever happens at the end of the day, I'm standing here, I'm sort of sensing a lot of different things. I can hear a lot of different things, and I'm obviously seeing and I'm talking. So it is amazing that my brain is able to pay attention to the task which is relevant, right? Something which none of these when the AlphaGo, and there's nothing to say that AlphaGo was a very good achievement, but when the AlphaGo, or even when Deep Blue played, the fact that the machine is just doing one task, one could argue that the person who was standing there could have been affected by some other task, could have been affected by some, maybe he was not feeling well, maybe not. I'm just giving an example. This is not an explanation. So when people talk about the status of human versus machine, I don't think it should be taken as just numbers, but it should be taken in a larger context than just comparing humans and machines. Having said that, it's undeniable that deep learning and these models have transformed the world. There are applications all over, including the application that I'm going to talk about now, which is in the application in the field of fashion. Right? So we are going to talk about, we sort of realized a couple of years ago in IBM that basically what was happening in e-commerce was that people were moving away from an online warehouse mechanism to where, you just go sort of click on certain things you like. More or less, firstly, you know what you're looking for, right? White t-shirt or blue t-shirt, and you sort of start with that, and you know where you're starting from. And people want to get away from there, and they want to have an in-store experience. So think about it if you're sort of going to let's say, a slightly higher-end store. Not from Bangalore, but let's say in Delhi, some of these local stores which sell suits or something, right? So when you go in, the assistant helps you a lot. They look at there are assistants who can tell you your waist size or this thing just by looking at you, right? People who have had that experience. They can sort of say that, for different kind of people, they can say, oh, because you're tall, these things will look better on you. You're sort of bulky, these things might look better on you. It's different, So a good assistant does really help you. And based on what you're wearing, they might definitely help you and say, okay, if you have a gray pant, most probably, let's say a white shirt or something like that will go with you, right? So what you want, what people have realized that you just don't want a dry search, right? When you go to an e-commerce site, what you want is something that not only is an engagement, like the engagement that the shopkeeper or the shop assistant is doing with you, right? You want discover, search, recommendation, and all those kind of things built in. You just don't want a very dry search experience. So what eventually we want to get to is a conversational system, much like this shop agent that I'm talking about, a cognitive agent that can help you sort of say, okay, these are the things that you might like. Then if you say that this is something that I'm going to use this for, then the person responds, the agent responds and say, okay, maybe these are the other refined results that you might be more interested in, and so on and so forth. So this idea of a conversational system that you could give both language, natural language, and vision inputs to, right? And it could respond to any of those. That's what you want to build eventually. Now, what we're going to talk about in particular are going to be just towards this conversation system, because I'm going to talk about only the computer vision systems. There is work. We are also doing work on the natural language side, but I'm sort of going to focus again just on the vision things. So the first thing that we are building, or first thing that everybody desires is something very simple, which we call the visual browse use case, right? Supposing you go into a store, so forget about the thing. It's very simply that you go into a store, you like something which is in the racks, and you just ask the person, do you want to show me some more of those, right? I like something blue, and you like the blue t-shirt, and you just want to see more blue t-shirts, right? And the person then picks out more blue t-shirts. So this is just like going to a store, figuring out, looking at things, and you initially don't have an idea. You're sort of starting from the store experience itself. So that helps a lot in many cases. It also helps. One of the best use cases is when something is out of stock, right? You like something, but it's only on the mannequin out there, and it's not there in your size, and then you say that, okay, can you find me something else which is there in my size, which looks very similar to this? So this use case is simple in the sense that it starts from catalog images, which are very well defined. They're very well focused, the lighting is very nice. This is a very good example. If the model is standing in a very nice pose, there's not much of a variation to it, right? So this is the visual browse use case towards this, these kind of interactions. The visual search, on the other hand, would be that you just take something, a photograph from the street, right? So in this particular example, you'd sort of like Sonam Kapoor's green dress, and you say that this is something that I want to buy, right? So in this is where the interaction is started, not from you're walking into a store, but this is where you've already made up your mind when you go and you have the query that you want to start off with, right? And this query could, as I showed earlier, could be in various different complications, right? The person could be standing in a different pose totally. It could be, as in this particular case, the background is quite overwhelming. You see actually the results sort of seem to match the background more than they match the color of the dress, right? So the visual search use case is quite complicated in the sense the input image could be very, very different, very different and could have lots of different variations. The other very important thing is in the visual search use case, the difference between the visual search and browse would be, in browse, because you're starting from the catalog and you assume that the catalog is fairly well defined and there are similar items, you're quite hopeful of getting a quite decent result. You already know what the results should look like, right? Yeah, and don't think of this as a mathematical result or algorithmic results. Think of it as an shopping experience, right? In that use case, you're more or less sort of sure what you'll get something close to what you're looking for. In this one, depending on, maybe you show this green dress to, say, a lehenga store, you'll get something very different. You show it to Zara, you'll get something very different, right? So this is not from the catalog. The search results will be very different, right? And the ability to quantify them, that this is a search result which is very good, is also quite difficult, right? Just by the fact that you don't know what is it really that you're looking for, and whether it exists in that catalog. So what we are doing basically is, and I'm going to show basically a couple of these things. So we are using deep learning models to learn this. What are the challenges here? The biggest challenges here is basically the data is limited, right? You expect a catalog to be about, the biggest catalog we have is about, at any point in time will be about 30,000 items. We are not working with Flipkarts and Amazons who might have a much larger catalog, but we are working with retailers, different retailers who might have at any point in time about 20,000 images. They will have about 5,000 units or items in their catalog, and maybe 20,000 odd images, 4 poses of each image, right? And also the catalog gets refreshed periodically, right? Every now and then something goes out of stock. The other thing is the weather changes, things get out of stock. So you want a deep learning model which is able to sort of use this limited training set and sort of keeps adapting to the training set as it changes, right? So it's not that you can learn a very large this thing. One thing which is very clear, that the depth of the deep learning, this thing which is heuristic, which is very clear to anybody, is that the depth is sort of, if you don't have, your training data and the depth should be proportional. If you don't have enough training data, you can't really train a very large deep neural network. You can do fine tuning, which is what we also end up doing. So the challenges here, as I said, are basically trying to figure out what is the methodology to fine tune some deep learning network with this limited amount of data and get reasonable results, right? More than just sort of learning to classify, as I said earlier, what you really want to be able to do is to learn invariances to certain things, right? So pose invariance and background invariance are one of the two most important things for both the pose invariance for the visual browse case also, and the background invariance for both visual search and visual browse. You basically want to be able to ignore the background and still get good results. You don't want basically the red carpet of the Sonam Kapoor image to overwhelm and not get any green dresses, right? Similarly, like in the pose invariance is very important because, for example, if you look at this, what I'm showing out here, this is a visual browse use case. There are 4 examples of the same dress, if you're not able to get those different poses, then you're sort of not having a very good algorithm, right? So this dress is there in four different poses. You should be able to return all 4 poses. So those are the kind of things, those are the interesting challenges here. How do you basically learn some kind of pose and background invariance? How do you build that into your model, right? And you could do a lot of different things, but to the extent of 3D modeling and all, but you could also do something simpler and try to use the multiple images that you have. Another thing that we are trying, and this is, catalogs are usually, one great thing about catalogs as compared to other images that you get out there is they're fairly rich, right? In both, they're fairly rich in the nice images, usually multiple images of each item. But they're also rich in terms of the text associated with them. They usually will sort of give a very descriptive, this thing, for example, here they've said pink floral print top, right? So you get you get the color, you get the pattern, you get the class label and all. So how do you basically use both the text query and the image query, right, together? So you have how do you use both the image and the text data together? So that's one interesting this thing. So basically, it's a joint learning such that you could query with either the image or you could query with the text. So what you want to learn is a joint embedding, right? So these are kind of work that also is going on. So in this example, we can sort of use any of the images and come up with, so you see a lot of floral tops that you could come up with, or you could use the text and you could come up with different results using the text query, right? Now the most complicated, the most interesting example is what is called the visual fashion tags. See, fashion is very interesting in a different, again, because of the depth of its attribute space, right? So here, let's take this example of this lady. You know, so you could have, if you would sort of really label this image, what you would need is to first figure out what the different parts of the images are, where the apparels are, right? So, and then given the apparels, you would want to find out the attributes. So each apparel out here is fairly, as I said, attribute rich. So for example, the skirt is white, it is fringe, it is short, it has knee length, the boots are brown, leather, tail, and high heel. So you have it's not that you just not only have the label, you have a very rich attribute space to work on, and you want to use that attribute space, right? So you want to be able to come out, because somebody might be interested in the top, somebody might be interested in the skirt, somebody might be interested in the boot, but that's what you want to be able to eventually use deep learning kind of models to be able to tag not only the labels, firstly segment the images, then to tag what the apparels are, and then find out what the attributes of the apparels are. Towards that, we are basically using these RNN models which are able to read from the image. So we have these deep learning models, and we basically then on top of it are RNN which learns, given this input tags, it is trying to learn what all is there in the image. Now, currently we are not using any attention or any localization. We are not doing any segmentation. So in this example, basically what would happen in our RNN, we would have an input tag like skirt, handbag, shirt, blue shirt, brown boots or something, and we are basically going to use the RNN to sort of output that same set of visual tags. So that's one thing that we are trying to do. But eventually what you do need is, which we have we are not using localization, but we want to be able to build fairly good localization models, right? In this particular case, you want to be able to say, here's the skirt, here's the shirt, here's the boots, and so on and so forth. Another thing that is very interesting is is the use of cognitive prints, right? So we want to, specifically this is very interesting for the Indian use case, right? So India is actually a large, I don't know the number, but it is a large producer of prints, right? There are lots of different companies here which do a lot of work both in the north and I'm sure in the south also. And these people basically use, so we were talking to one of them, and the mechanism to sort of do prints, come up with new prints is sort of look at old prints, right? This is true a lot in fashion world in general, which is basically a lot of work is done by using inspiration from previous. So what you're wearing now, most probably was also being worn, let's say, in the 60s or the 70s or 80s, right? And then it's come back after 20 years, 30 odd years, and similarly for the prints, people go back, look at the catalog, they like a couple of prints, put them together and sort of say, okay, this is the print of 2017, right? Something like that, of that sort. So what are the kind of prints that you could generate? Can you do the similar kind of, can you look at previous catalog? Can you sort of mix two prints together and come up with prints which will be relevant for this age and this time, and which you might have some other hints, you might put in some other hints, like what is the dominant color for this year, what is the, is there a fashion trend that you could sort of latch onto? So these are the kind of things that we are doing. We are basically trying to use generative models. We are getting some texture information, but we need to sort of get more and try to figure out try to make this better and better in terms of this thing. As I said right up front, the eventual goal here is to build a conversational system, right? So what you want to say, and this is an example of a conversation system which is multimodal. So you could either be you could either be interacting using natural language, or you could be interacting using images. And you would be on the left side, you're getting the query results and you're showing what are things that are useful. The agent would be using fashion trends, it will be making recommendations, it will be doing search, it will be doing some kind of this thing to basically engage the user. And this is what the eventual goal of the IBM Cognitive Fashion project is, to get to the stage. Now all this is good. The other thing about it is some of these, quite a few of these things are already deployed. None of these things are possible, as I said, without systems, right? You can't sort of just say that I am going to do all this and there's really no system in place to deliver these models, right? Nobody's going to come to your website and sort of spend minutes or order of minutes to sort of type in to get responses for complicated queries, right? So you want to be able to ensure that your systems are good enough to be able to respond in real time and give a good user interaction. Very simple diagram here, and the only reason I sort of put it out there is because each block of this becomes crucial. So whether it's the extract feature, which is what your deep learning model would do, whether it's the nearest neighbor indexing, how do you build the nearest neighbor, all of those things become useful at some point in this thing. And basically now with Docker containers or these Kubernetes, everybody is moved to that. There's Bluemix architecture which allows you to do this in a fairly nice and easy manner. You could deploy these different components in different parts of different containers and then sort of stitch them together to deliver the API. Now, all this is definitely very good, but there's still something which is even more, you'll have to get a little bit deeper into, which is basically, deep learning models don't come for free. They are expensive. And what I'm showing here is the energy profile. So right on the top is a chart which basically shows what the joules per year consumption is. 2010, so what was the energy production, and what do the current systems use, the joule that they use per bit, right? So current systems use about, I think this thing was written in 2015, they use about 10 to the minus 11 joule per bit. So that's what they use. The target system that people want to go to, so if we continue with the benchmark system, we'll run out of computing. Computing will exceed the energy production. Like computing will take more power than what energies we produce in 2035 or something of that sort. People want to go to 10 to the minus 17, and then the limits are 10 to the minus 21. The reason I bring up that is everybody's concerned about energy. This is not this IBM, or there's not, if you talk that the chart on there's Google, there's Microsoft, there's this thing, especially when you talk about deep learning, right? These really large models, each of them are doing something, and you're basically a lot of processors, lots of weights, lots of parameters that are being processed. So people are concerned about the energy consumption of deep learning networks, and they're sort of going to hasten that in some sense increase the slope of that, so that if we don't find better systems, we are going to run out of energy in some sense. It's not going to happen, but just for the sake of argument. We also, in IBM, are trying to reduce it. So one of the important things that we want to do is basically increase we want to decrease the inferencing time and increase the, maintain the accuracy, decrease the memory footprint of our inferencing systems, right? So we want to have a base code of Caffe would take about 40 megabytes of memory. We have got it down to about 197 megabytes. The inferencing is much improved. And so this is the kind of work that you want to do, because this has a direct impact on the energy and the cost that you're going to deliver to the throughput is going to have a direct impact on how many images that you can process, and the memory and other things will have a direct impact on the cost to the user, right? So there is a lot of work on basically optimizing the energy, this thing, and this sort of brings me back in a circle towards the biological brain. So what is the most efficient machine out there? As I said, and I still sort of maintain, it's the brain, right? It basically, you can fit it in a 1 liter bottle, and it consumes about 25 watts of power. And it does so many things. It's not that there's a brain which is just doing smell, or there's a brain which is just doing talking, or there's a brain which is just doing hearing, right? The brain by itself is doing all these different things. So there is a very large, beyond what, till now there had been a lot of work, a lot of inspiration from the brain towards artificial neural networks for improving the accuracy of, say, the computer vision model, or increasing accuracy of the speech recognition model, increasing the accuracy of the NLP models. But there's going to be increasingly a large amount of work going into how do you improve the efficiency and get the efficiency towards what the brain efficiency is, right? You want to make these models more efficient in terms of power and energy. One of the efforts, for example, I'm not going to, is in IBM, there's a chip called True North, which basically is a synaptic chip which consumes very little power, 45 picojoules per spike, and is able to do some of the deep learning things. This is a chip in progress. It was sponsored by the Defense Agency in America. It's something that hopefully will come out in a couple of years from now, and have very good performance in terms of deep learning models. Also, very good performance in terms of energy consumption. And by that, I conclude my talk with some code that I find quite interesting. Sure. Anybody's questions, comments?
So we are talking about improving the accuracy of output or the model as such, right? I think very less work has been done in terms of creating a self-learning noise reduction system. So is there any work which you guys think you have worked on that?
No, I think, yes. So a lot of the work that has gone in, I've sort of not gone into that detail of, a lot of work has gone into supervised learning where the cost function is being minimized. And what you're talking about, self-learning or unsupervised learning kind of mechanisms are less explored till now. There is some work, or I think every group out there is trying to do more and more of this kind of work, because in some sense, supervised learning is a solved problem. You could, for computer vision and all, you could say that fairly easy to say to classify images. Unsupervised learning is not a solved problem at all, and a lot of different folks are working on it. We have efforts in that direction, basically in many different areas. For example, in vision, we have some things on ICAs and using like component analysis and those kind of things. I'm sure other people also have similar kind of efforts.
Hi. Hi, Raghavendra.
Question to make. Actually, you've spoken very well on the fashion and image mapping and stuff. So I was just wondering whether there are some innovations happening around, body fitting and all. Because the primary problem around fashion and shopping is whether the garment is going to fit me or not. Yeah. So is there a mapping or something that you're thinking of having a, body fit, hair color, hair size, skin color and stuff like that, so that it can be more cognitive and it happens to be more actual?
Yeah, very good question. I think, so there's a huge amount of work actually going on in that area, not only because of the things that you mentioned, but also because remember that returns are a big problem for everybody, right? Return is a cost. So if you send out something and it doesn't fit the person, it comes back, it's this thing. So we also are attempting, so there is like how do you really map the body into a certain this thing, right? So there are various things. One is body measurement, how do you do better? One is also the idea of that, as I mentioned right up in front, that you say, okay, I sort of classify this person as a tall person, let's just say. And in on a tall person, I sort of figure out from sort of either data mining, that these are the kind of things that have been, other customers have used well. So this is a very simple example, right? So some kind of a clustering based on body proportions and all that. But there's definitely a scope for a lot more work.
Because the one that we've seen right now did not entice me at all. And maybe if you could have shown something around my body figure and something that would suit me exactly, I would get enticed and I would buy the product immediately.
Yeah, so I think it's a more challenging problem also, right? And the question becomes also of, do people upload their own images? There's a lot of different issues that come up. So the kind of interactions that we are currently seeing are interactions with catalog images or images of celebrities, right? People often don't upload their images. We haven't sort of come across that many examples. We haven't come across, we have come across people who talk about body shape with respect to return, like body sizing with respect to return, but we haven't come across people saying, okay, there's a selfie uploaded and then sort of start the interaction from there. So it depends upon what I agree with you that that's a very enticing use case, but it depends upon what people are sort of providing us.
Hi Raghavendra Prasad.
Hi.
This was a nice talk. So regarding that million images to train, in terms which we don't do for the human baby. So why can't we think in a paradigm shift like genetic way of like how you have highlighted here? Because I can support that theory also, I can refute. Like million images, I can say the baby would see things in like 24 to 36 frames per second. By the year 2, it would have seen billion images. That's what most of the computer vision scientists say. Why can't we, have a different paradigm shift rather than having this kind of a, compute intensive which is not yieldable at this point of time?
Yeah, so I think, so let me first say this, that the million image, what I meant and what I want to clarify with that particular statement is that it's not that the baby does not, over the time period we see a lot of images, right? But we see images, not each of them are supervised that this is an apple. So we get a lot of different clues, right? So maybe it happens, let's take a simple example, the baby sort of picks up a red ball and tries to bite on it, and that gives it a clue that there's a ball, not this thing, right? So one of the things that what learning, and people are trying to do this, is sort of learning with clues, right? You just don't learn with supervision. This is sort of related to self-learning question that was up front. So that's where like the million versus not million and all those things come from. I definitely agree that there's genetics is going to be something that we are predisposed towards certain things. We have enough knowledge which we come by. We should be able to use it in a much better way. And I'm sure there are people, for example, Jiten Malik in California, Berkeley, and other people who are starting to look at this child psychology and things before it to understand what we already have as a kid, as a small child, and how can we build on top of that. So I think there's going to be a lot of more work on that area.
Hi. So you talked about at the beginning of your presentation of how a human brain synapse has a timestamp. Can you elaborate on that? Okay. As in what is it used for, and how can we incorporate that in a deep learning network?
So the difference between in the neural networks that we are using right now, the DNNs, we basically have a value, right? So that, remember the ReLU function?
Right.
So basically, if you're greater than 0, you will send out the value itself, 2, 3, whatever. The synaptic, the human brain has an impulse, which the only value associated is the time. So what happens is in the brain that basically you get a burst of spikes or you might get a rate-coded spike. So you might say there's different patterns of spikes that come, and the patterns are in time. And basically, that's what the brain uses as a value, rather than sort of saying the value itself is encoded in the impulse, right? So the interesting question here is that, so spikes allow your system to be event-driven, which lowers the cost. So that's one of the fundamental things here. Event-driven systems are lower than the clock-driven systems. All systems that we are talking about nowadays are clock-driven systems, right? So clock-driven systems are like 1 by 1, whatever, 5 gigahertz we'll process. Event-driven system are that whenever some event happens, we'll process. So that's the thing. The challenge is how do you really do it? So which is a challenge which is ongoing.
Thank you.